Hello everyone, and welcome to video 5 of chapter 7, and probably our last video unless we have questions that I will address and post online if they come up. So we are now moving from talking about finding z-values, x-values, and probabilities to assessing whether or not a dataset is normal. Once we know it's normal, then we can use those tools we've covered so far in class in the first two sections of this chapter. But we don't know that yet, so we need to confirm. So you hopefully have already read this. We will use this table, as it says critical values for correlation coefficient. So today I'm first going to show you, we're going to look at two examples. We're going to look at how to generate them in StatCrunch. And the thing you need to know is that you can't generate the actual R values that we're looking for in your calculator easily. So if on the test you may be asked to do it in StatCrunch, which I'll show you how to do that, or you'll just be asked to interpret. Okay, so we need to interpret. By interpret, I mean use this critical value table that you see here and draw the proper conclusions based on that. Okay, so here, as it says, I'm not just going to review it here. If the linear correlation coefficient between the observed value and the expected XZ scores. Now, this is something that's going to sound really complicated because we're not actually going to calculate each of those values. We're not talking about the regression that we've done so far. We'll talk about that more later, not in this chapter. But we're talking about a special plot that's created just to check this. Okay, so it says here, it says it's difficult to determine this if you just visually look at it. Okay, because we're looking for a linear line. We want the points of the probability plot to fall on a linear line, but it's hard to tell just by looking at it. Okay, so here what we're going to do is use this table to calculate a value, or StatCrunch will do it for us, and then use this table to draw whether or not it's statistically normal enough or not. Okay, so our first example here is this one. So we've actually seen this data many times before. We have eruption times, 15 of them from the Old Faithful Geyser in California. Is it reasonable to assume the time between eruptions is normally distributed? Okay, so I've already copied this data into StatCrunch. Okay, so this is the data here. Okay, so what we want to do is we've used the word probability plot. The other name for that is called a QQ plot. So here, and it's called QQ for quantile. So I'm going to click QQ plot. I'm then going to put over my variable, and I'm going to click this add correlation statistic. That's the statistic we're going to use to be able to test formally whether or not this is normally distributed. So I click compute. Okay, so here we have the normal quantile on the bottom. That's okay. Eruption time on the left. Okay, so I'm going to in a second show you how to do this plot in the calculator, but what StatCrunch only will give to you is the correlation up here at the top. Do not confuse the correlation between two variables with this correlation. This is the same notion, but it's between two variables that we know what one of them is. The other one is something that's been calculated for us. So it's kind of hard to look at. So here, 0.913. So what we're going to do is we're going to go look at the table that we just had and decide whether or not we think this is normally distributed. So you should stop and think before we even look at those values. Do you think it is enough? And what I mean by that is does it fall on that line? Do all the points fall approximately close to that line? Because I would say, notice the one down here in the bottom left corner that are in the one in the top right, that maybe that's not true. So here we have a R value of 0.913. And we're going to go to the PowerPoint to that table. And we're going to find our N value. Our N value is 15. Okay, so here this table is actually only going up to 14. Okay, so we're going to use the 14 value for the moment. And it says 0.592. So what we're looking at is if our R value is bigger than that, okay, then we are going to say that it is not approximately normal. Okay, so if it's bigger than that, it is not approximately normal. So here, our R value is quite a bit bigger than that. So we're going to say for this example, it's not approximately normal. Okay, so next example here, and we see this here, the time between eruptions is likely not normal, 0.913. Okay, so we can then ask ourselves, why is it not normal? Well, we can look at a box plot, and we'll notice that there is, in fact, an outlier here. So that outlier may be likely causing that lack of normality. So one researcher would then go investigate, what is that outlier even? Is it real data? Is it mistaken data? And maybe they remove it, maybe they don't. Okay, so there could also be other distributions than normal. Our next example here is similar, different data, but we're going to do the same process here. Suppose that 70 randomly selected workers at the detergent factory were tested for exposure to this enzyme by measuring the ratio of forced expiratory volume, to vital capacity. Note that FeV is the maximum volume of air a person can exhale in a second. Vc is the maximum volume of air that a person can exhale after taking a deep breath. It is reasonable to conclude that the ratio of those things is normally distributed. That's the question. Okay, so at this moment, I would suggest that you pause the video and see if you can answer that question without me first talking about it. Okay, so if you paused it, great. If you didn't, that's okay too. So here, I'm going to, again, I've already copied this data into StatCrunch for us. This is the data right here. I'm going to do the same process, graph, QQ-plot. I'm going to put over the variable here and then include the correlation statistic. Okay, so here, these points more regularly fall close to the line. We don't have any that are really far away from the line. They're mostly close to this red line. Okay, so the statistic is 0.98. How many points do we have is the question. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Have now found what I was looking for, which is the entire table that we have before. And as I thought, there's definitely an error in the PowerPoint, so I will get that fixed. So our previous example here, we had this plot here with the correlation of 0.913. So now flipping to the full n value table here, this is from our textbook, we go to n equals 15 and it's 0.514. Okay, so because our value is not smaller than that, we actually can assume that we do have normal. So even for this first example, even with that outlier, it is actually approximately normal still. So even with these outliers, it still comes up as approximately normal. And the reason for that is the majority of the data is in here. Okay, the majority of the data is close to the line. Okay, so back to this new example where we were looking at in StatCrunch, we just did the plot here. So that's this guy here. Okay, so it's our new example with the enzymes. We have a correlation of 0.98. We now have 16 data points. Okay, so here, 16 data points, we go to our table right here. 16 data points has this critical value of 0.9497. Certainly 0.9 is not smaller than that. Because 0.9 is not smaller than this, we agree that the data is approximately normal. Okay. So just for comparison's sake here, what I'm saying is from our current example, okay, here's the plot. This looks different because it's from something called Minitab. So let's look at the one on here, and I'll put the correct one in there for when I post the notes. Okay, so here 0.98. Okay, so 0.98 is not less than. Not less than the table, the value from the table. Okay, so the value from the table here is 16.497. It's not less than. So then this tells us normal. That means we get what we want. Normal. Okay? So that is how we use that table. So